Kia ora guys, so this is for question 2 of the NCEA complex numbers paper from 2017. So let's get straight into it. Okay, so we dividing x cubed minus 2x squared plus 5x plus d by x minus 3 gives a remainder of 13. Find the value of d. So we've got a bit of a clue here. Dividing. Oh shucks, that's thick. Okay, I checked it. So what we're going to do is we'll just set up some long division. So I'm going to go x minus 3. And then in here we're going to go x cubed minus 2x squared plus 5x plus d. Okay, so I want to make my thing a little tidier. Okay, so what we do is we say, what number do I need to multiply x by to get x cubed? So that is x squared, not a number at all to be honest. So x times x squared, and then we just do it on the line below, equals x cubed. But then we also have to do minus 3 times x squared. So that becomes minus 3x squared. Then we just draw a line down here. And so we say this minus that, and that's always going to be 0 because that's why we chose x squared. And then negative 2x squared minus negative 3x squared. So that's like doing plus 3x squared. So that leaves us with x squared. Okay, we've also got to carry everything else that's left over. So we're going to carry this down, plus 5x plus d. Okay, so x squared, another way to think about it is x squared divided by x. What's that? That gets us positive x. So that means we're going to go x times x will get us x squared. Then negative 3 times x, that gets us minus 3x. Nice. So then we go down here and we ask, what is 5 minus negative 3? So that gets us to 8x. And then we'll carry down that d plus d. Final step, so we're going to go x times 8 gets us 8x. We'll go plus 8. And then that's going to get us our 8x. But here's the thing, negative 3 times 8, that's negative 24. So what happens here is we actually know our remainder. So we're actually sort of heading towards this number 13 here. So we know that d minus negative 24, so that's d plus 24, is going to get us a leftover of 13. So therefore we can say that d equals negative 11 by just doing minus 24. And that's that one. Cool. Simplify as far as possible in question B the expression root of 2k and then brackets root of 18k minus root of 8k. So first thing I'm going to do here is I'm going to split up the root. I'm splitting up the root because of the rule that if we have a, b to the power of n, that is a to the power of n, b to the power of n. Right, and in this case we can just, it's like we're looking at 1 over n or 1 over n. Right? Okay, so it's going to be square root 2 square root k, and then that's going to be multiplied by, now square root 18. I can see something nice in that already because I know that 18 equals 9 times 2, and that's the same as 3 squared times 2. Don't be afraid to use like some of your page to do some of this working out. Also, let's have a look at that 8. 8 is the same as 2 squared times 2. So we can do surds here and drag out a 3 from the 18 and drag out a 2 from the 8. So I'm going to do that now. So I'm going to drag out that 3 root, and the leftover is a 2, and then we're going to go root k. And then the next one, we're dragging out that 2 root 2, and then we've got our root k there. Okay, so the next step, I should probably put an equal sign up here. is I'm just going to multiply out. Now the thing is, when we do root 2 times root 2, that gets us with a 2, and then 2 times 3 is 6. So it's going to be 6. Square root k times square root k is just k. And then root 2 times root 2 is going to get us a 2 there. 2 times negative 2 is negative 4. And then root k times root k gets us another k. So we are left out with 2k. Looks pretty simple to me. Okay, let's move down. Question C. Z and W are complex numbers such that Z equals negative 2 plus 3i and ZW equals 15 minus 3i. Find an exact value of the argument of W. So there's a couple of ways to go about this. What's the best way today? Yeah, let's just go this way. So what we know is that ZW, well, what we could do is we could make up a W. We can say that W equals X plus IY. And we know that if we multiply this here with that, so Z with W, that will get us this. So we can do a little bit, we'll see how it goes. What do you think if there's a better way to do that? I'll settle with this. Okay, so Z first, negative 2 plus 3i, and then W, maybe I should write this here, X plus IY, and we know that that's equal to 15 minus 3i. So let's expand this. I'm actually going to expand it in such a way that I get all of my real numbers on the left and all my imaginary numbers on the right, and I'll show you how I do that. So I'm going to multiply the first two, so it's going to be negative 2x, but then I'm going to multiply the two imaginary parts. So that's 3i multiplied by iy. So the I times the I makes it a negative, so then that's going to be minus 3y, and notice that that's our real part. Now let's do the imaginary part. So negative 2 times iy makes negative 2y, and then I'll chuck the I on the end, and then 3xi, so we'll go plus 3 xi, and that equals 15 minus 3i. So then what I'm going to do is I'm just going to have a look at the imaginary part and the real part separately and see if we can build up some simultaneous equations. So see how I've got this imaginary part and this real part, and then over here I've got imaginary part and real part. Now this actually, it comes up I think in every paper that you have to do this sort of split thing. So what I'm going to do is I'm going to equate these things with each other. So I know that negative 2x minus 3y equals 15. And I also know from this red section that if I was to factor out an I and then get rid of that I can say that negative 2y plus 3x equals negative 3. So this is my real part, and this is my imaginary part. And that just makes us a simultaneous equation. So what we'll do, what one looks like it's easier to make into the subject? None of them look amazing, to be quite honest with you. I might have a go. Let's just do this side, doesn't really matter too much. So what I'm going to do is I'm going to shuffle things around a little bit. Negative 15 minus 3y equals a positive 2x, because I wanted to get rid of that negative sign. Then I'll just divide this side by 2. So negative 15 minus 3y over 2 is equal to x. So that's ready to be substituted into here. Looks a bit ugly, but let's see how she comes out. So over here I'm going to change it to negative 2y plus 3 times all that gear. Should I do that all at once? I'll show you the substitution. Negative 15 minus 3y over 2 equals negative 3. Let's scroll down a bit. Hopefully I've got some space. Not too much. Okay, I'm gonna multiply everything by 2 because I can't be bothered dealing with that right now. So at the same time as I do some other stuff. So that's going to be negative 4y Sometimes I like to do this notation. I like to write this. I'm timesing everything by 2. Okay. Plus, oh no, it's going to be minus. So I'm going to go 3 times 15. So that multiplying by 2 just gets rid of that, which is way easier. So 3 times negative 15 is negative 45. And then 3 times negative 3 is minus 9y. And that equals negative 3. So I've got 13y. I'm just going to shove it over here to make it positive. And then I'm going to bring my negative 3 over here, make it into a positive, but that doesn't help too much. It becomes negative 42 equals 13y. I've made a mistake. Oh, I didn't multiply my 3 by 2. Nice. How did I know I made a mistake? Because these numbers aren't related to each other, and most of the time in complex numbers you come up with fairly pretty answers, at least with surds or imaginary components. But I forgot to multiply that by 2, so that should have been negative 6, which then changes this to negative 45 plus 6, that's negative 39. Aha! Those numbers are related. So now I know that y equals 3. Once I know that y equals 3, I can substitute into this one. Negative 15 minus 3 times 3 over 2 equals x. And then that becomes negative 24 over 2, negative 12 equals x. That's x, that's y. So therefore w equals, how do we define it? We defined it as x plus iy. So it becomes negative 12 plus 3i. Maybe do that for your marker. Let's double check that I got that right. It's not what my page says. Seems right to me. Okay, cool. Let's move on. So, question D. Solve the equation z to the power 4 equals m over root 2 plus m over root 2i, where m is real and positive. Real and positive. Interesting. Okay. Write your solution in polar form in terms of m. Okay, so I'm going to start off with a picture. I'm going to draw 2 pictures for this one. Now, what we know is this number is real and positive. So even though it's divided by root 2, that's going to remain on the being real and positive. So on the real part, we know that that's a positive number. So we're going to have this here, and that's going to be m over root 2. And then what makes this question nice and easy is the fact that on the imaginary part of the Cartesian plane, we know that that is also m over root 2. Right? So we've got this here, which is z to the power 4. And we can actually get this and translate this into Cartesian form really easy. And the reason we want it in Cartesian form is because we need Demar's theorem to solve this. Oh, come on. Okay, so we can actually work out the argument really easy because it is an exact quarter, because this is a square, right? So because it's a diagonal along the square, we know that this is exactly pi over 4, which is very handy. Now we can sit and we'll work out the modulus. So that's going to be m over root 2 plus m over root 2i. And to work that out, all we need to do is get the square root, and then we're going to square both of these things. Now, that's easy because it's m squared over, and the square of square root 2 is 2 plus m squared over 2. Now, conveniently, that means that it's m squared. Yeah, that's it. It's just the square root of m squared. Square root m squared, because there's 2 of these, and they're halves, and that means it's m. So we've got our argument, arg of z4, is that nice enough? Yeah, equals pi over 4, and then mod z4 equals all this stuff. Make that separate. So now we have our Cartesian form ready. Z to the power 4 equals m cis pi over 4. Very convenient numbers and letters they chose there, which make this question pretty easy. Okay, so for Demar's theorem, all we have to do is we treat this algebraically. So we do m to the power of 1 over 4. So z to the n equals m to the 1 over 4 cis, and then what we do is we divide this pi over 4 by 4, so it becomes pi over 16. And it's the other thing we do is we add on that little kicker of 2k pi over 4, but then we've got to sort of translate it. So it's going to be 2, remember how we have to add on our little 2k pi kicker? Now the reason we add that on is for rotation, because up here, one solution will be in one direction, but then we've got to consider the fact that if you did a whole rotation, there's another solution there, and we need to 4 solutions overall. So then there's going to be another rotation, whoop, that gets us to here, and then there's going to be another rotation, whoop, that gets us to here. Wait, how many have I got now? 1, 2, 3, 4. So that's why we're adding on 2k pi, because 2 pi is a full rotation, and the k is just however many times we need to go around. In this case, it's 4 times total, right? So now, 2k pi, we have to divide that by 4. When we divided this by 4, we have to do the same thing. So that becomes 2k pi over 4, and that becomes, what does that become? We kind of want to make it like sort of like this one here. So what I'm going to do is I'm going to times that by 4 again. So I'm going to make it 8k pi over 16. Just makes it way easier to deal with. 8k pi over 16. Okay, so that will be able to give us all of our solutions if we just plug in some values for k. So we're going to go from k equals 0 up to k equals 3, which will give us 4 solutions. So k equals 0 is the easiest one, so we go z1 equals m to the power of a quarter, or the 4th root of m, cis, and then it's just the basic pi over 16. Now, let's draw a picture of what that looks like. Zing. Zang. Okay, so right now, where is my little thing? Pi over 16 is tiny, because it's actually going to be like that. It's probably not amazing. And that's going to be Rm to the power of 1 over 4. Let's have a look at our next one. Z2 is m to the 1 over 4. So the modulus stays the same. Oh, okay, I'm going to try and draw that circle again. Oh, that's not too bad. I'm kind of happy with that. No, my rubber sucks though. I'll make that smaller later, don't worry. Okay, so this is our first solution, Z1 here. Z2 is m to 1 over 4 cis, and then we're just going to substitute k equals 1 here, so that becomes 8 pi over 16. 8 pi over 16 plus pi over 16 equals 9 pi over 16. Now, 9 pi over 16 is just, well, what's halfway is a pi, right? Halfway is a pi, so 9 pi over 16 is just over halfway to halfway. So it's going to be here. That's Z2. Now, I can, from this, I know there's 4 solutions, so these are actually just going to split into quarters. So I can actually just draw in my other ones, and then I can check if my solutions that are coming out are correct. So that's going to be Z3, that's going to be Z4. This will also help me when I'm trying to put it into like being a nice positive or a negative. I might make this one a negative argument. So Z3 equals m to the 1 over 4 cis, and then what happens is I go 9 plus 8, that gets me to 17 pi over 16, which is the same as if I was to rotate here 15. So I'm going to go negative 15 pi over 16. Beautiful. Z4. Let's try do this one without thinking, eh? See how it's just before? So that means it's going to be 7. Negative 7 pi over 16. Now let's check it. Negative 15 plus 8. Boom, negative 7. Beautiful. So those are our 4 solutions. Now, I want to do a little bit of explanation. So you can see that our Z4 is here, and we explained the fact that we got one solution here, and then another solution from one more rotation, another solution from another rotation, another from another rotation. This translates in here as our Z1, 2, 3, 4, and the spacings between these will always be proportional to how many there are. Right? Okay, cool. So let's see if there's any more questions in this. Okay, cool. Find all possible values of k that make u equals k plus 4i over 1 plus ki, a purely real number. So let's just remind ourselves what purely real numbers look like in our imaginary world, our complex plane. So we've got imaginary up here and we've got real here. So all of these, this whole line here, this is all positives, but they only care about purely real, so we include 0 and all the negatives. So we're just looking for this blue space here. Okay, let's have a go. That make this a purely real number. First thing we're going to do is we're going to try and get rid of imaginary numbers that are on the denominator. It tends to be the way to go. So we do that by doing the conjugate. So we get k plus 4i over 1 plus ki. So let's do the conjugate. We'll multiply that by, we get that number, but we flip the sign here, minus ki. And to make that multiplying by 1, we just keep them the same as each other. So let's do that. What happens here is 1 times 1 gets us 1 squared. Then we get k times k is k squared. I times I makes a negative. So a negative, negative, so that becomes a positive. So that's going to become 1 plus k squared on the base. I don't know why I did the base first. I shouldn't have really, because now I don't really know how much space I need on the top. Okay, so we've got, this is a little bit ugly, so I'm going to do it on a table because I'm prone to making errors, so I much prefer to deal with it like this. K, 4i, 1, negative ki. So it's 1 times k is k, 1 times 4i is 4i, k times negative ki is negative k squared i, and then negative k times, negative ki times 4i is going to get us to 4k. Reason being, it's a negative, and then that I times I makes another negative. Okay, so I'm going to split that into imaginary and real parts as well. So my real part is 5k, and then my imaginary part is plus, I'm actually going to do this, I, and it's negative k squared plus 4. Now, the denominator is real. So we actually don't really need to worry about it. And also, this here is real. So the only thing that we need to worry about is, when is this 0? When is this 0? Because it matters when that's 0, because then I times 0 means there's going to be no imaginary part. So all we need to do is negative k squared plus 4 equals 0. Right, so let's make that positive. 4 equals k squared. And then let's just do the square root, plus or minus. Square root of 4 equals k. So that is plus minus 2. And that's it. Those are all the possible values of k that make u a purely real number. Alright, that is question 2 done. And one more video will come out with question 3 very soon.